Here's our outline for today. I want to start with just a few comments concerning exam X, which is coming up next Tuesday. Just to go over the basics for you, and I know everybody's a little nervous about it since we did have the hurricane, and it is kind of a combo exam. So remember, we're going over a little bit more information on this test than a normal midterm. And so I'll have the same number of brain burners, but there'll be proportionally more basic questions. So for most people, it will seem a little bit easier than if you had taken 2 midterms from me like last spring in astronomy 2002, or the equivalent to midterms. Let's see. Raspberry colored Scantron, 50 on each side. It has the Pegasus logo, the UCF Pegasus logo on it. Number 2 pencil and a good eraser. Now, when I say good eraser, this is the kind that I mean. One of these pink jobs from 2nd grade, okay, because I've noticed that the built-in erasers on most pencils these days just tear up a Scantron, and you do not want to do that. Also, try to get to class without getting your Scantron all crinkled up. I mean, I had some students a few semesters ago, they turned in a test, a Scantron that was returned to me by the grading guy, the guy that does the computer grading for Scantrons, could not be graded. Wet. Disgusting. So try not to sneeze on your Scantron during the test or anything disgusting like that, because they won't be able to go through the grading machine. But otherwise, you should be good. Calculator, like maybe one of these jobs costs you 15 bucks. And if you don't have one, you'll be able to do your work, like 6th grade long division on pencil and paper. You should be able to handle it without too much. Remember, there's not going to be a huge amount of time pressure for this exam, even though we're making it even bigger than the original plan was. So everything's going to work out good. Bring your clicker. I still have not decided if I'm going to use clicker questions on this test. I might do it. Make sure to bring it. We do have clicker questions in just a few minutes, so make sure your clicker is on. And if you haven't used your iClicker yet in this class, hold the power button down until the rectangle flashes, and then type in D, delta, delta, and that will synchronize you to the session. And let me just remind those of you, if you have looked at your grades page and you still have a 0 there for participating, do not be deceived. Just getting a check mark and a Go Nitro does not mean you're registered. What means you're registered is if I put that you have a 1 there in the participation row of your grades page. That means I'm getting data that I can connect to your NID. That will not happen if you don't register your iClicker in web courses. All right? You can't do it with iClicker.com. That doesn't synchronize to our roster. Okay, so you've got to be registered through web courses. And if you don't, you're not going to get any dinero from participating. Okay, so which is what you want to do. It's a big chunk of change. So bring your iClicker, Scantron, pencil, eraser. You'll be able to write on the test. All right, so don't worry about, should I bring scratch paper or anything like that. Just bring your stuff and your pencil and your calculator and your iClicker, and that should be good. Now, we don't have a lot of formulas in this class, but you might want to make a note about how we do handle formulas on exams. You know, a lot of students come up and ask me, hey, Dr. B, are we going to have a formula sheet for the exam? And my answer to that is no. No, we don't have that. But what we do have is for the first 2 or 3 questions, 3 or 4 questions, 4 or 5 questions, we have some matching items. And I'll give you, you know, like a few formulas or equations. And then on the right, you know, A, B, C, D, E and stuff, like a description or the name or a bunch of names or some kind of a concept that you'll connect to that formula. And that way you'll have the formulas you'll need. And it won't be a formula sheet, but yet you don't have to memorize. All right? And you just have to recognize. All right? So the formula sheet does not exist, but a few formula questions, and usually they're pretty easy. You know, you'll recognize them. And we haven't had a huge number of equations yet. And for the most of the semester, we won't be doing a lot of equations like a regular physics class. But yeah, we will have a few. So expect that for the first, you know, 3, 4 questions maybe. And that'll be good. If we do have clicking, it will be the last 2 or 3 questions, and they'll be separately printed on the last page of the test. The clicker questions might be 1-point multiple choice items that I want to keep track of through the iClicker. See, the iClicker allows me to grade. I grade the iClicker results. You know, the Scantron guy grades the Scantron, which is nice, but sometimes I want to look at specific data and see how you're following. And so I look at the spreadsheets for every single person, and it's fairly easy to grade. So when you're doing the iClicker questions, if there is a calculation, it might be 2 or 3 points. If there's a multiple choice iClicker question, that'll be 1 point, just like the Scantron multiple choice and matching and true false. All right? And so we may have like 45 Scantron questions and 3 clicker questions, 2 2-point calculations, and a 1-point multiple choice. Okay, so be aware of that. Okay, and I'll try to announce over the weekend if it's going to be no iClicker on the test. But assume for now that it will be. And make sure your iClicker, by the way, make sure your iClicker has some good batteries in it, especially if you bought it used. Because the batteries that come with the iClicker when you buy it are really El Cheapo batteries. And if they flake out in the middle of a test, which they are prone to do, you are SOL. Okay, so put some Duracells or some energizers in there, and and that'll be good. Question? You know, even if you bought it new, just don't take any chances, because they're just really cheap, and you have no idea when they're going to fail, and so either that or have a couple spares in your book bag or whatnot. Any other questions? Yes, Sydney. At the observatory. How do we submit proof that we went to the observatory session for extra credit? I am so glad that you answered that. And because I know everybody, I want everybody to go. Did anybody look at it this morning, by the way? The schedule page? Is there anything going? Do they? Tonight? No, tomorrow night. Is there anything? Are you on it right now? Yeah, be alert for tomorrow night or something like that. I don't know if that's on the schedule. Is there something on the schedule for this week? Are you looking at the schedule now? Is he? In any event, if we do have the extra credit observing session, Sydney, what you'll do you'll go to the session, and the students. It's a student-run operation, and so students from this class that join the Astronomy Society, and from other classes, and they run the session. And what they'll do is they'll give you a handout, 2 sides. You'll put your name and the date and that kind of stuff, and who your instructor is or what section you're in. And then you'll record your observations on the observation sheet. Right? So if you're looking at the moons of Jupiter, you'll make a little sketch of Jupiter and the moons and what you see. And then you'll hand it in to the guys running the session. All right? And so and then what they'll do is they'll sort out all of my students and give me a big pile of handouts, hopefully, of all my students' observation sheets. And then I'll go and look at that, and I'll give you bonus points based on those handouts. So that's how it will work. It works pretty good. It's not, but the one thing about it, it doesn't work rapidly. What's going on? October 5th, so that's next Thursday. Okay, so nothing going this week apparently, but next Thursday maybe. Hopefully the weather, because the reason I'm asking is the air is really dry back on the backside of Maria, which is off the coast of Virginia apparently right now. So we should have some good seeing tonight. Go out and do some stargazing tonight if you want. Go look for Orion. Question?
For the exam, will he post like some kind of review, some kind of summary of things?
What's the answer to that? No, your lecture notes are your study guide, okay? And just so you know, if I don't mention it or touch on a subject in lecture, then it's not, or if it's not in the reading, primarily lecture and then secondary readings that I assign, then it won't be on the test, all right? And, it's a decision that I have to make every day, of all the zillion things that we could spend an entire semester just talking about the moon. And there's zillions of guys working down at Mission Control in Houston that's what they've done for their entire careers, is study the moon, right? So I have to make a decision every day about what to put on. And so I try to choose the important stuff. And then on an exam, I'm trying to see if you guys savvy the important stuff. So the important stuff is going to be mentioned somehow in lecture. All right, so go by your lecture notes. Go improve them, use YouTube and stuff, and that'll be good. So, but no study guides from Dr. B. Any other questions before we continue with clicker questions? Just a side note, you may have, in case you messaged me in web courses over the weekend, I did not get back to Orlando till late Sunday. I had to go out of town for a funeral, family funeral. And so that's why we didn't have any extra homework. I promised you some homework Thursday. And if you messaged me, I haven't even looked at any of the, the messages. So if you did message me, I'll be getting to it. I didn't post anything on the internet about participation or anything like that because I was just occupied. But anyways, we'll get ready. We'll continue on with this week. And let's mention what we did last week. Last time we talked about we started talking about Kepler's 3 laws of planetary motion. The first one is basically that planets travel on an ellipse. And Kepler deduced and kind of calculated out that, you know, it's an ellipse, and an ellipse is not necessarily a circle. As you know, a circle is a special form of an ellipse, perfectly symmetric. But the sun is not at the center of the ellipse where the two axes intersect. The sun is at a focus, which is, you know, a special point on an ellipse. And actually, every ellipse has two. The other focus is empty. And you may say, well, does that mean that there's a secret planet there at the other focus? The answer is no. It's just a geometry has a little bit more information than what nature uses. Nature just uses the one focus. And we'll talk about that in a minute. We also talked about the eccentricity. We did a little calculation. There's the formula down there. We had vocabulary terms, perihelion and aphelion. We'll talk a little bit more about that today. The other two laws are called the equal areas law, and we'll talk about that in a few minutes. And then the third law, an orbital period and semi-major axis, that's the big one. That's the really useful one. And we'll be talking about that in just a few minutes. So that's just a little recap of what we talked about Friday, and you can listen to the YouTube, not Friday, but last Thursday. I want to draw your attention to figure 3 in the free textbook at OpenStax. This figure is nice because it shows how to construct an ellipse on paper using thumbtacks and like a bulletin board. If my TA was here, I don't know what happened to her, we would be able to do it on a marker board. But you know, you can, if you just go draw an ellipse string draw in Google, you'll come up with, you know, probably dozens of videos of people doing the very same thing. And it's pretty cool. And it's all related to semi-major axis and semi-minor axis and stuff like that. So go ahead and look at figure 3 and read about it in chapter 3. You know, and that's good backup enrichment of the stuff that we talked about concerning ellipses. Because this red dot here is the center. Let me get my cursor here. This red dot in the center, that's the center. That's where the major and the minor axes intersect. But that's not where the sun would be. The sun would be at one of the thumbtacks. The thumbtacks are at a focus of the ellipse, and an ellipse has two foci. So, all right, clicker question. Here we go. This one's by way of being a visual IQ test, and I'll give everybody the correct answer on this one, but just vote with the answer that you think is right. Which orbit below is a perfect circle with eccentricity exactly 0? Orbit 88, orbit K. Are they both perfect circles? Is neither a perfect circle? Now look carefully and make a decision. And this is a short answer question, so you have to type in A, B, C, or D, and then hit the send key. Okay? And a bunch of you have done that, so take a minute to do that. And you know, no matter what you send in, I'll grade it correct. Okay, so don't worry about that. Just give me your best thought. I want to see what your visual perception is and your visual decision making. Which one, or are they both, or is neither a perfect circle? Eccentricity 0. All right, 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, 263 of yous. Okay, let's see what we got here. Yeah, this is interesting. Let me switch over here. Here's the distribution of the answers A got 14%, B got 11%, C got 32%. What was C? That's both. D is neither. That got, nobody had none of these four options had a majority. That's interesting. Let me switch back over here. Laptop. Okay. So D got the most, but guess what? Who voted for orbit 88? Geniuses. And not many obvious. But everybody, I'll give everybody a thing. Now, this one over here, that's Mars. Orbit K is Mars. And remember last time I told you that it's an elliptical orbit. It's fairly elliptical for planets, but still hard to determine that it's not a perfect circle. Yeah, this is, and I'll show you show you why that works. So here's a comparison. All right, now this is eyeballs only. Orbit 88, the yellow one, the way that you can tell that this one is a perfect square, is a perfect circle, is you can scribe in a perfect square around it and no daylight at the sides or at the bottom. All right? Now, I'm going to try to do the same thing with the orbit of Mars. All right? Now this is, you know what? I may ask you a question about this on exam X, a visual version of this, like a multiple choice. Now, here's the square. Now, can you see the daylight at the bottom of this? Right down here? You see that? Just a little smidgen of daylight. And that's what Kepler saw. You can't see, when you look at it on YouTube, you'll be able to see it. I'm sitting up here really close, and it's even just a tiny smidgen. But that is what Kepler was able to detect. And so when he said, boy, these things, they're actually ellipses, ding, that's how skillful his calculation and his eyeballs were. He saw that daylight, right? And so when we talk about planets being on an elliptical orbit, it's pretty darn close to a circle. Now, comets, asteroids, there's a lot of asteroids out in the asteroid belt that are on circular orbits, pretty close. But then there's other asteroids that loop in close to the sun, that far out, and a lot of comets that do the same thing. But planets, yeah, and most of the moons are in the solar system are pretty close to circular orbits too. All right, so that's a clicker question for now. Now let's take a look at the second law. This is Figure 4 from Chapter 3, 3.1. And here's there's a lot of different ways to state the equal areas law. And notice that this one, I've got the focus, this is for an ellipse, for like a comet, but it's also true for, how the heck did he figure out this for Mars? That is astounding to think about it, because Mars is so close to a perfect circle. This, it's easy to see. So in two different time periods of equal duration, the amount of area that's swept out by the radius that goes out from the sun out to the planet, it sweeps out equal areas. Now, if you look at this, it's two different shaped wedges. One of them is real slivery, and one of them is almost 90 degrees, all right, of a pi wedge. Right? But wedge A over there is real slivery, right? But it's longer. It's out there at aphelion, and so that's the aphelion wedge. And then the perihelion wedge is really, it's not as wide, but it sweeps out more degrees. All right. So as a planet moves around its orbit, It sweeps out equal areas at equal times. All right. Now, the reason for this, and you can write this down, Kepler did not know the physical reason for this. It took another 50 years or so for Sir Isaac Newton to bag this. But Sir Isaac Newton figured it out in the law of universal gravitation. And he found out that the reason for this is that at perihelion, the planet is moving really fast because it's closer to the sun. And closer to the sun means stronger gravity. All right? So make a note of that. The whole reason for the pi wedges to be different shapes, really slivery at aphelion and really wide at perihelion, is because at perihelion you've got a faster planet or comet, and at aphelion you've got a really pokey one. So for note B here, at aphelion it's very pokey because gravity out there is kind of weak. Right? And gravity is the weakest force in the universe. But it's all pervasive, it can't be screened, and it can't be switched off. And it's always attractive. It's the force of the four forces of nature. It's the one that we have the hardest time figuring out, especially in terms of quantum gravity. Anyways, here's a close-up. So down there at aphelion, over here, that's where you're going fast. You're really whipping. But then over here at aphelion, all right, it's, you're still moving, and it's moving faster than the fastest jet aircraft, and I don't care what jet aircraft they have. If you're a planet, you're moving faster than that, all right? So like the SR-71 Blackbird, forget about it. All those fancy new ones that got up in orbit, forget about it. This is still faster than them, but compared to the rest of the orbit, that's the slowest point. All right, so you have a really thin wedge of area, and in actuality, and make a note here, there's an entire range of speeds. The speed is always changing. All right, the maximum speed is down at perihelion. The minimum speed is at aphelion. All right, so make a note of that. Slowest, minimum speed. Perihelion, fastest, maximum speed. But if you're over here at some intermediate point, like just go ahead and choose a point down there on the lower part of the orbit, anywhere is fine. Right there you've got an intermediate speed, somewhere between the minimum and the maximum. All right? And gravity in this one is going, let's see, what is that? Counterclockwise. Okay, so this comet is going counterclockwise. And down there where it says medium, that square down there, it's on its, go ahead and make a note. The comet is on its way to aphelion. At that part of the orbit, it's on its way out. It just looped around over here at perihelion, so it was really moving over here, Alex. And then down here, it's on its way back out to aphelion, so it's kind of slowing down. All right. So the speedometer rating is biggest here, and it's still pretty good down here. And then the speedometer, you're talking the granny lane over here. All right. But now, go ahead and I don't have it on the screen, but you can put another intermediate dot up here somewhere. All right. So this would be point D. All right, and it could be, you just put it anywhere up there. All right, now on that upper half of the ellipse, the comet has passed aphelion, and now it's heading back down towards the sun. And this is usually where we see new comets, when they're out, they've started inward toward perihelion, because when they get to perihelion in the central part of the solar system, they start to reflect a lot of light, and they blow a lot of gas because it gets really hot, and it becomes visible to us on Earth. And we can see comets way out past the the orbit of Mars and Jupiter. But they're pretty small. You have to have good telescopes. But by the time it gets down here, down to the middle of the solar system, very bright. Okay. Raise your hand if you've ever seen a comet. We've had a few lately. I've even taken photographs of comets. It's amazing. Anyway, so your intermediate point up here somewhere, anywhere, it's on its way back. So now gravity is speeding it up. Right? So it's getting faster and faster. And faster until it gets down here to perihelion. And then it hits the maximum speed. And then it's back down on this, the lower half. It's back out towards aphelion, slowing down again. So you have speed up, slow down, speed up, slow down. Every cycle. Question? No. We're only going forward. But on YouTube, you can go and look at, and repeat and review what I just talked about. Hopefully, if it records. All right, so here's another view of it. So because of the speed, the perihelion is where you have a wide swing, a lot of degrees. Depending so this would be like 1 month. This is like 30 days for some comet. This is a pretty, this is actually more like a near-Earth object than a real comet. Anyways, so this is a hypothetical 30-day period in here. Pretty wide swing if you're at perihelion, but then really slivery, just a few degrees of swing for that wedge out there at aphelion. But theoretically, those areas are equal. And let me tell you, the area of an ellipse is fairly easy to calculate, but I would not want to do the calculus for this to compare, 2 30-day periods on any ellipse. But I'm sure that there are plenty of guys that do it. But it'd be pretty rough, even for Sir Isaac Newton. Now, second comment here, or another comment, if this were a perfect circular orbit, like orbit 88, then each 30-day period would sweep out an equal-sized piece of pie. Right? And if it was a 1-year orbit, that would be about 12 pieces of pie every year, all the same size. Right? If it was a perfect ellipse. And here's the kicker. You know what? Most of you messed up. You didn't get the right answer for the clicker question that we just did. And so, in other words, you were not able to tell that Mars was not a perfect circle. To you, it looked perfect. But somehow, Kepler figured out and deduced, well, my pie slices here are not quite the same size, but oh my goodness, they had to be really, really close. So that's Kepler's second law. Equal areas, a lot of fancy calculus and physics behind it, but visually it's fairly easy to understand. Any questions on this before we continue? Raise your hand if you're an ed major. Any secondary ed or elementary ed majors? I love ed majors. Okay. You may be thinking, Dr. B, why do you, when you ask for questions, why do you always just wait like 2 hours for people? And it's not 2 hours, it may seem like that, but what I'm doing is I'm using the 15-second rule. And for those of you that are ed majors and become teachers, especially for older students, like college or high school, the 15-second rule is whenever you ask for questions, this is something one of my first physics profs in grad school taught us. When you're in lecture, You ask for questions, give the students 15 seconds. And I could do it. I have a timer going on my screen here. And so here's 15 seconds, starting now. "15 seconds. It seems like an age, but it's just 15 seconds. And the theory is that when you give students 15 seconds, they usually ask a question. But nobody has a question now, so let's keep going. Kepler's third law, and this is the big one. This is the one that astronomers use all the time, not just in the solar system, but in any binary star system. And in fact, we've got the solar system wrapped up pretty good. We're still figuring some things out, way out past Neptune and Pluto and stuff, but we know most of the solar system pretty well. And this is what Kepler deduced. That the planets orbit the sun obeying this precise mathematical relationship. That the square of the period P is equal to the cube, the third power, of the semi-major axis. All right? And our textbook uses the letter P, capital letter P. And so in the solar system, this is Kepler's third law. P squared equals A to the third. And for this law to be exactly this, you have to measure the period in Earth years. Okay? So, so some astronomer on Mars could use a Mars year, but then he'd have to use the astronomical unit defined by Mars's orbit. And then he would find that this is still true. All right, so measured in Earth years, and the Earth-Sun distance, semi-major axis, has to be measured in astronomical units. So for Earth, that's 1. And the orbital period for the Earth, that's 1. Now, it's cinchy to say that 1 year squared and 1 astronomical unit to the third power, 1 squared is equal to 1, and 1 to the third power is equal to 1. That's cinchy. But it actually works out for all the other planets, and you can check it out on, like the planetary data sheet. So like Mars, I think, is about 1.5 astronomical units, something like that. And Saturn is about 5, if I recall correctly. I don't have those memorized, but you can look them up. They're in your textbook. They're all over the place. Now, if you don't use Earth years and astronomical units, and you don't have to, then there's a whole bunch of other constants that come in. And that's something that, as I said, Sir Isaac Newton figured out all the physics of Kepler's 3 laws. He figured out why the forces of nature guarantee this law is kosher. All right, and I'll show you those extra constants. There's a factor of pi, and then there's the mass of the sun and the mass of the planet and stuff. So it's a little bit trickier, but here's another diagram. So this one, the average orbital speed in kilometers per second is here, and the average distance from the sun is here. So that's another way to look at it. It's kind of Mercury is really going fast, and then by the time you're out here to Saturn, you're still going pretty fast, but much slower than Mercury. All right. Now, what I want to discuss with you. Oops, my animation is a little bit messed up here. This works for any binary system. And this is what Newton nailed to the wall. He came up with 3 laws of motion in the latter half of the 1600s, so a little bit after Kepler. And he also came up with the principles of calculus. And when you do that, you come up with this particular formula. This is the formula that works for any binary system. 2 planets orbiting, or 2 moons, a sun, a star, and a planet, 2 stars in a binary star system. And we've talked about those. Now, and I'll explain why it is so simple if you do it in astronomical units and years. But if you're not using years, if you're using days, which a lot of astronomers use for the orbit of planets, or even years, and if you're using, instead of astronomical units, if you're using light seconds or light days, some astronomers do that, then you've got to use this formula here, okay? And so in the numerator there, go ahead and write this one down. We're not going to make any calculations with this, but we're going to talk about those who have done calculations with this. But I still want you to see it. It's kind of bodacious. The numerator is 4 pi squared, so a bunch of calculus gets you to that. And then capital G, that is Newton's gravitational constant. It's also known as Newton's constant, or the gravitational constant. And believe it or not, that is the constant that rules the strength of gravity. All right, Newton introduced it in his formula for, which is in your textbook, for the universal law of gravitation as a conversion factor. But it actually ends up being involved with, for instance, the size of black hole event horizons and stuff. So capital G is actually started out as a conversion factor and is now viewed as having fundamental importance in theoretical astrophysics and relativity. M1 and M2, that's the mass of the 2 objects in your binary system. So like the mass of the sun and the mass of the earth. M1 for the sun, M2 for the earth. And we'll do a calculation with a simple ratio calculation of that in a minute. But it could be, star 1 and star 2, like Sirius A and Sirius B. And that's basically how we figure out this, plus being able to observe the size of the orbits allow us to figure out the mass of the 2 stars, and we use it all the time. And on Thursday, I'll show you a calculation for Sirius, and I think I'll try to dig up the numbers for Cygnus X1. But Sirius, and you can do it for any double star system you want. Now, this, and note D here is, this is how we detect black holes. Because if we can figure out how many kilograms of mass it has, and how small of an orbit it has, we can see, well, theoretically, that's got to be a black hole. It might, if it's not that small, it might be just a big star that's cooled off and doesn't really give off any visible light. But if it's not, if it's really small, yep, we can figure out that it's a black hole. Now, how did Kepler miss this factor? This is a question from 3.3, when talking about Newton's law of universal gravitation. So part of your reading tonight, if you haven't already done it, is to review chapter 3.3. In units of sun's mass, the sun's mass, the mass of the sun is 1. The units of the sun's mass, the mass of a typical planet is a negligibly small factor. All right, now what they mean by that, we're going to do it not in terms of the solar mass being 1, but in terms of kilograms. All right, so here's the mass of the sun, M, and then there's a little subscript there, a circle with a dot in the middle of it. Okay, that circle with a dot in the middle in the first equation, that's the symbol for the sun, a circle with a dot in the middle of it. And the mass of the sun is about 2 times 10 to the 30 kilograms. All right? Now, a kilogram is the mass of a liter of water. And so this is 2 times 10 to the 30. Okay, 10 to the 30. What is 10 to the 30? Let me think here. Okay, 10 to the 3rd is 1,000. 10 to the 6 is 1,000,000. 10 to the 9 is a billion. 10 to the 12 is a trillion. 10 to the 15 is a quadrillion. 10 to the 18 is a quintillion. 10 to the 21 is a sexotillion. 10 to the 24 is a heptillion. 10 to the 27 is an octillion. 10 to the 30 is a ninotillion. Whoa. A 10 followed by 30 zeros. I don't know. I don't even know what they call that, a ninotillion. I mean, an octillion, I know what that is, but I don't know what they would say for the 9, for the next set of 3 zeros. Anyways, that's how many kilograms for the sun. Now, the Earth is 6 times 10 to the 24 kilograms. And that's a big pile of kilograms. Okay, so what was 24? Let's see. 3 is 1,000, million, billion, trillion, quadrillion, 5 tillion, 6 tillion. Okay, so the mass of the Earth is 6 heptillion kilograms, and that's a ton of kilograms. The Earth's got a lot of mass. All right, that's why your feet are on the floor instead of floating around in the air. If we had a smaller planet, as a matter of fact, we do have a small planet, the moon. We've sent guys up there, and when you look at the films of the Apollo astronauts up at the moon, they can jump, way up in the, they can jump and cover like 30 feet in the air. It's amazing. Now, what we want to do is calculate the ratio. So the ratio of m of the sun divided by m of the Earth. By the way, that circle symbol with a little plus sign in the middle of it, that's the symbol for Earth. Okay? And sometimes you'll see some books, they'll just write out the word S-U-N and the word E-A-R-T-H. But traditionally, these are the symbols, and it's a little bit more compact. So the mass of the sun divided by the mass of the Earth is about 333,333. Whoa. So that's how much more mass the sun has. That's how many times more the sun has compared to Earth. All right? Now, going back to this formula here, let's see. In the denominator is the sum m1 plus m2, so that could be mass of the sun plus mass of the Earth. All right? All right? And so the point being that with this ratio, the sum m of the sun plus m of the Earth is pretty close to just the m of the sun. So the number of kilograms in the denominator of the full accurate Kepler's third law, m1 plus m2, that number of kilograms is pretty much the same number as the number of kilograms of the sun. All right? And for that reason, all the other constants work out to be 1 if you use astronomical units and Earth years in the equation. So it's not unusual for Kepler to have not seen that factor. He couldn't figure out the mass of the planets and stuff. But Sir Isaac Newton was the one that made the breakthrough for that by coming up with the law of universal gravitation. Let me pause for questions. Yes? I'm going to make you do that? What's the answer to that question? Yes or no? No. I already explained it, yeah. Yeah, I want you to see it, but you're not going to have to make calc. And I want you to understand why this is true, right? But we're not going to, I don't even like making those calculations, so, but I want you to see it and see how complicated it is and why it's the numerator, or excuse me, the denominator is pretty much the same as the mass of the sun only. Now, side note, and actually I'm glad you brought that up, because it gives me a chance to give you a side note. If you are working with two comparable objects, like two stars, then you'd have to use that formula, and you couldn't neglect mass number 2. With the sun and the Earth is so small compared to the sun, just, round it off to the mass of the sun and call it good. But when you're looking at two stars or a black hole and another star, baby, you cannot round those off. They're going to be the same order of magnitude, so you just got to, calculate with them. But it's possible to do it, and you guys won't have to do it on the exam, but at least you'll see that it is something to consider, the separate factors. Now, here's an example where we use that. The black hole, SGR A star, Sagittarius A star, and its companion S2. Now, take a look at this. Just make a note. Dr. B's blabbing his big mouth about another black hole in the center of the galaxy. He talks about it every day, just about, yeah, it's an important one to know about. And there's a lot of cool physics involved with it. S2. Now, these are infrared images, black and white, grayscale, of the center of our galaxy. And we can't really see with visible light down in there, but infrared we have a fairly good handle. All right, with the right infrared telescopes, you can bag this. All right, now, if you look carefully, right here, there's a little rectangle outlined in black at the center of this image. All right, now here's a blow up of that rectangle. There's a blow up of it. Now right here, right down in here are the two objects, S2 and SGR A star. Right, here's S1, here's S8, here's S4. By the way, let me go back to this one. See how they have down here 10 seconds? And what does that say? 0.39 PC? That's a parsec. I'll be teaching you guys about that next week. It's a distance unit like a light year. But look at this one. Down here, this arrow down here, maybe a third of the width. That's 1 second of arc. And that sliver of angle, by the time you get, by 1 second of arc, by the time you get to the back door here of the lecture hall, would maybe be a couple inches. Maybe. But by the time you get to the center of the galaxy, that corresponds to 46 light days. Right? So make a note of that. 1 second of arc is 46 light days. And if you can get that figure, if you can get the size of the orbit, i.e. its semi-major axis, in light seconds or AUs or light years or whatever it happens to be, you can use Kepler's third law. Right? If you can map out this orbit, this is the one that we've been looking at, right? This is the same one, SGR A star. This is a simplified diagram of the positions that they calculated by looking at infrared. If you can get the semi-major axis, and that's what they've got right here, 0.119 arc seconds. That's 119 milli-arc seconds. Go ahead and make a note of that. The semi-major axis for star S2, 119 milli-arc seconds, and that corresponds to a certain number of probably light hours, I'm guessing. And I should work that out. All right, and then this circle with the plus sign in the middle of it, that's SGR A star. That's the actual black hole. And here's the orbit. So if you can get this, it's always fairly easy to get the timing, because if you follow it for so many years, you can You know, like this one, they started following it in 92. And then by about 2002, they said, yeah, we got enough data. We know this orbit. We know the timing. And now we also know the semi-major axis. We can use Kepler's third law. And that is why these guys were able to find that the mass is about 3.7 million times the mass of the sun. All right? They were able to figure it out. Now, a couple other things I want to mention to you about this. Here's the period, all right, for S2. This star, this ellipse that's going around, and this is a fairly eccentric ellipse. In fact, you can see the eccentricity is 0.87, right? They got that too, right? So they follow this thing for about 10 years, and they said, you know what? I'm very confident of my ellipse. It's 0.87. My period's about 15.2 years. That's close enough for government work. Let's get an estimate on the central mass of the black hole. And that's what they were able to figure out. So we've already mentioned the semi-major axis. All right. Oh, and you know what? I did figure out what the semi-major axis is. It's about 5.5 light days. All right. Now, 5.5 light days is much larger than the orbit of Neptune, much larger than the solar system. The outer planets, you're talking light hours for light to travel from the sun out to the outer planets. For us, it's just 8 minutes. For the outer planets, it's measured in a few hours. Light days would be a pretty big orbit. So this is still a pretty big orbit, all right? And the star S2, it's happy as a clam out there. It's not going to get sucked into the black hole. And you may be saying to yourself, Dr. B, I thought everything got sucked into the black hole. No, no, no. It's attracted gravitationally, but it might not. I mean, only when you get close to the event horizon. That's the point of no return. And I calculated that too. The event horizon for this is 37 light seconds. Right? So this black hole down there is 37 light seconds across. And that's the point of no return. If you get even if you get 38 light seconds, there's a good chance you're going to get sucked in, unless you have ultra strong rockets. But if you get to 37, it's over, man. You're toast. You're getting sucked in there. But S2 is out there, 5.5 light days. It's just, it's out there, singing a song, having a nice day, eating Snickers and Pringles and watching TV, watching Netflix, binge watching on Netflix. So there's no problem with that. All right. So S2 is safe for now. It's about 13,000 times the size of the event horizon. The closest approach, periastron, that's down here. Periastron means close to the star, astron. Peri means close or above, astron, star. So the point of closest approach down here is about 1,700 times the event horizon. So S2 is good. All right. Let's keep going. Here's another pair of orbiting objects. This is Sirius A and B. We'll go through the calculation for this. And we don't actually have to use this equation, but we're going to leverage this equation on Thursday for Sirius A and B. And look at those two times, 1999 and 1950. Here they are, right up here, right? And so the whole idea here is it's fairly easy to time an orbit if it's big enough. You can measure its position over the years. But getting the semi-major axis in light seconds or anything else is kind of difficult. Okay, Questions about black holes and Newton and Kepler's third law before we continue. And this is an open period for black hole questions. Yeah.
Unless you said it, I missed it. How far is the light second?
How far is a light second? It's the distance that light goes in 1 second, right? Okay, and a light second is light moves at 3 times 10 to the 8 meters per second. So 1 second of light travel is 3 times 10 to the 8 meters. That's 300 million meters. Okay, 300,000 kilometers. And there's about 500 of those between us and the sun. 93 million miles. So let's see. 93 divided by 500. Can somebody do that? 93 divided by 500? I don't know if I can do it on this calculator here. 93 divided by 500. Who's got it? What do you got? Okay, 0.186 million miles. Yeah, that's right, 186,000 miles per second. That's the speed of light in miles per second. Not miles per hour, miles per second. You know, the fastest orbit spacecraft, you're talking about 20,000, 17, 18, 19, 20,000 miles per hour. You know, when they launch in low Earth orbit. And that's a minuscule fraction of the speed of light. Another question. Speed of light, black hole question. Yes? The question is, do black holes stop growing or do they just keep growing? The answer to that is yes, no, or maybe, multiple choice. And it depends, and I'm not being facetious, but it just depends on the environment around the black hole and how it forms. Like SGR, A star, is probably growing and has grown to the current 3.7 million times the mass of the sun. It's probably gobbled up entire stars down there at the center of the galaxy over the eons of time. Now, we don't know how those galactic black holes form. We have an idea about how, like Cygnus X1, we think we know how that one formed. You know, the result of some kind of a detonation on the surface, either a supernova or some other detonation that left behind the core of that star that was so heavy after the detonation, you know, because the detonation will compress the core, and it'll form a core of iron if it's a supernova, and then if it's really heavy and compact, it'll just keep crushing down, and it might form a neutron star, but if it's really, really large, greater than 1.4 times the mass of the sun, it'll just keep going and form a black hole. Now, if that happens for a star like our sun that doesn't have any companion, we're not part of a binary system or anything, okay? If there was a big star that went into supernova and left behind a black hole, but it didn't have any companions, and there's many that are like that, then it probably won't do much. You know, that's it. But if it's near a companion like Cygnus X1, it's sucking, the reason we can see Cygnus X1 is it's sucking stuff off the surface of the star that we can see. You know, we see the star orbiting it. We can't see it. We see a source of X-rays, and the X-rays are basically the outer layers of that giant star being sucked off by the intense gravity, and then they spiral around. They're heading for the black hole event horizon, and along the way, they get hotter and hotter and hotter because they become so hot that they emit X-rays. Now, it's one of the interesting facts of, are you listening? I'm about to say something that will confound that you can use to confound your enemies and amaze your friends. All that stuff that's sucked off the surface of that giant star, we will never see it actually enter the black hole. Our time, our clock, will go to infinity before we see that stuff go into the black hole. However, if you were an astronaut riding with a blob of that surface, the plasma pulled off the surface of the sun, and you were on a spaceship and you sacrifice your life for the life of science, and you'd be going into the black hole, your clock would move a finite amount of time. You'd be there in like 2 days or a year or 30 seconds or whatever it happens to be. You'd see the inside of the black hole. You'd get there. But here on Earth, we will never see you cross the event horizon or any of the stuff, any of the hydrogen and helium sucked off the surface of that star. And the reason for that is the curvature of space-time and the weird things that happen at the event horizon, which we'll talk about this semester. And that's just a little introductory mystery there. Another question. Okay, I'll set up a little bit more reading assignment in the next hour or so. Look for it, and I'll see you on Thursday. You're dismissed.